Okay, so let's talk about limits. We're going to kind of do an introduction and then talk about how to find limits from graphs and tables. I know we've talked about this before, so I'm going to actually introduce this like we haven't talked about it before. All right, so let's start. So pretty much, what is a limit? What's the point? So think about this. What if we had a geometric series, right, that was halved each time? So the ratio for this geometric series is r equals 1/2. Right, so we have 128, 64, and every time we go one more term, we cut it in half. Right, so now this is a series, so clearly it's infinite, and clearly there's another number, but we've actually shown that this has a sum, right? So there's an infinite number of pieces, so it never actually, the series never ends, it's infinite, but we've shown that there is a sum. So if you add up all of these infinite terms, you get 256. It's actually a pretty nice sum. So the question is, how in the world is this possible? How do we sum up an infinite number of things and get an answer to a point that we never reach? And way back when, they solved this problem by thinking about limits. So this is true, and it's mathematically true that the infinite sum here is 256, and it's done from this concept of limits. So think of limits as a process that gives us an answer, right, or a value or an idea or information about some situation that doesn't seem like it ends or doesn't really have an answer. All right, so we model how the system behaves more than where it ends. All right. Okay, so also think about something like this. What if we had this function? So x squared plus x minus 2 all over x minus 1, and we weren't interested in this function around x equals 1. Well, if I plug in 1, all right, do substitution, I'll get 0 divided by 0. Because there's a 0 in the denominator, we know that it doesn't exist at 1. Well, is that it? Right? Is that what we do? We just put does not exist and move on. There's nothing else that really is interesting here. Is that the idea? Well, let's see. So if I were to graph it, you can see clearly on the graph, it even almost looks like the point exists. So just plugging in the number of getting does not exist is not enough, right? There's a lot of stuff going on here that is helpful to us, right? So at x equals 1, in fact, even though it looks like it exists, you don't see it's a single pixel, but really there's a single point there that doesn't exist, right? But look at how around that open circle it's a line, and it looks wonderfully neat and simplistic and all that good stuff. So what we could say is, hey, look, I know that at x equals 1, it doesn't exist. But around it, as it approaches that number x equals 1, the y actually approaches 3. And that's the next idea of a limit. It's that what's the behavior? So, what's the behavior of something that kind of doesn't exist, that doesn't really have an answer, if that makes sense? All right, so that's what limits are all about. Okay, so in your notes, I want you to write this down. So, the concept of a limit is just that idea. A limit represents the behavior of a function near a particular input. And I put near in red because we use terms like that, close, near, because we want to get very close to that input value. All right, and we can determine behavior by graphs and tables. Graphs are a wonderful visual way to see behavior of a function, and tables, although may seem a little more complex, are actually a fantastic way to be very accurate about seeing what's going on near a point. All right? Okay, so let's do an example. So here's this idea of a limit represents the behavior near an input, and we can do graphs and tables. So let's say I have this graph, and I can find the limit of any input, any x value on this graph. I'm just going to pick a few. So let's say x equals -3, right? That's that point down there. So I want to see how this actual graph behaves in that red oval. And it looks like in that red oval, as I approach -3, the actual y value, the graph approaches y equals -3. So the limit here would be as x approaches -3, y approaches -3. So the limit is -3. Well, what if we did x equals 0? So here's my x equals 0 line. Notice I have two things going on. This graph actually splits. So if I come in from the left, it looks like I'm going to go to 0. If I come in from the right, it looks like it's approaching 5. They approach two different numbers, so there's no limit here, right? So the behavior, that's a weird thing. The behavior I want to discuss has to be the same behavior from left and right, or there's no limit. Because what would you say? You could say that the limit is 0, and your friend could say the limit is 5. Well, clearly, if there's a choice, there's no limit, all right? All right, let's do one more. So you can see at x equals 7, we want to see what happens to this graph as I approach 7. It looks like it's constant. So it doesn't matter where I really am, right? If I'm greater than 5, it looks like the y value is always going to be -2. So I would say the behavior of that blue line around x equals 7 is y equals -2. Okay? All right. Well, we can do the same, complete classic problem 1. All right, so stop the video and complete classic problem 1. Okay, we can do the exact same thing with tables, right? So remember, we can determine behavior from graphs and tables. So let's start here. So let's say my first one was I wanted to know what happened around -3. So I do a table, I put -3 in the middle because that's what I care about. I go a little left of -3, I go a little right of -3, and I figure out the y values, the f of x values. Well, notice as I come in from the left, right, and if I put it in the middle and go left of -3, then if I come in this way, then that's coming in from the left of -3, and if I come in this way, it's from the right. But look, I'm really not sure what's going on here. I can definitely see a pattern. It looks like the x and the y values are the same. So I could kind of guess this is going to -3, but these are really, and I know it doesn't seem like it, but these values are really too far apart. So -4.5, -4, they're really I'm not confident is what I should say. So even when I come in from the right as well, you can see, I still can see kind of a pattern, and I can make a good guess, but I'm not real sure what's going on. All right, and so to be sure, that's what this near means. We need to be much, much closer to this value. All right, so on my table, I wouldn't do by 0.5s, and I'd make this a standard. I'd go to the left, 0.001, 0.01, and then 0.1, and then I go to the right, 0.001, 0.01, 0.1. Okay, and now you can see there's no more ambiguity. As I come in from the left, that's clearly approaching -3. All right, so see how -3.1, -3.01, -3.001, that's obvious. So I don't have this ambiguity anymore. So the closer I can get to this value of interest, this point of interest, the better the more accurate my estimation will be. And as I come in from the right, and that's clearly going to -3. So I'm very confident to suggest that the behavior of this function around -3 is -3. All right, so that's the take home. Be very close to the point, be very near to the point you care about. Okay, let's do some other ones. So I also did x equals 0 from our graph. So now I do a table of it, and you can see I'm very close to 0. So left of 0, again, 0.001, 0.01, 0.1 to the right, same thing. You can see as I come in from the left, it's very clear that's going to 0. As I come in from the right, it's very clear that's going to 5. So again, if you have a choice, it means the behavior is different left and right. Okay? All right, we can also do 7, right? And you can see just like we did our x equals 7, from the left was -2, from the right is -2. This one's easy because it's always -2, right? So the behavior looks like it's constant, all right? Okay, so here was the graph we initially found behavior for, and I just want to show you that how the table does the same thing. So here's the table for -3, and you can see how I approach -3 from the left, and I approach -3 from the right, and these numbers will show you this approach. All right, so try to visualize what's going on with the tables in these terms. So I'm below -3, and I come up to -3, below -3, come up to -3. I'm above -3 and come down, so I'm above and come down, okay? All right, at 0, you can also see, right, from the left it's 0, so it shows me this. Coming in from the right is 5, it shows me this. All right, so again, try to visualize what these tables are doing as graphs. And then lastly, the 7 was constant, and you can see that's what this showed. So it's -2 everywhere around here, and that's exactly what this table shows, -2. All right? Okay, so tables and graphs are wonderful. Graphs are a good estimation. They're not necessarily accurate because we're pulling off the numbers, but a table will be as accurate as you need to be, right? Because you can always make these numbers closer to this point. All right, so tables are good because for accuracy. All right, so stop this and complete classwork problem 2. Okay, so now let's do some notes here. So we have a notation for limits. So we pretty much discuss what limits are, its behaviors of functions. So now the notation is LIM, then we have a little subscript, x arrow a, f of x equals L. Now what does all this mean? First of all, let's see how it's read. This is red, so this bold is red. The limit of f of x as x approaches a equals L. All right, so limit of f of x as x approaches a equals L. That's how it's read. Let's go each piece. The lim, the LIM, just represents limit, and it means you need to find the behavior of the function f around the input. All right. The x approaches a. That gives you the input value of interest, and that means the input value here is a. So we care about what happens around a. F of x is simply just the function you want to investigate. And L is the actual limit, right? It is the behavior near the input. So think of L as kind of a y value, an output, right? But it really is the behavior of the function, which turns out to be, an output. Okay? All right, so let's stop this and complete classwork problem number 3. All right, let's do some examples here. Right? Well, an example, but we'll use a graph and a table, right? So I want to evaluate the limit of this function using graphs and tables. So remember, the limit is find the output or find the behavior of this function near this. So that's our first part, right? So this limit notation means what is the behavior of f of x, which happens to be 3x minus 1, around x equals 1, right? So what does this really mean? We want to find what y approaches as x approaches 1. We want to find the y value, the output, all right? Okay, so let's start with a graph. Let's do a graph. So let's graph it. Let's do our point of interest is right at x equals 1. I'll go up there. So this is what I'm looking for. So I have to decide what the behavior is as I approach 1. And it looks like as I come in from the left, I stop here. As I come in from the right, I stop here. So it looks like I'm stopping right at y equals 2. All right. So I don't care what it equals at 1. I care what the behavior is. And it looks like the behavior from left and right of 1 is actually 2. So I would say the limit of 3x minus 1 as x approaches 1 is 2. Right? Which again means the behavior as I approach 1, this function approaches 2. Okay? All right, let's try a table. So table, now we want the point of interest, which is 1. Remember, I put that right in the middle. Let's go a little left, and again, we'll go subtract 0.001, subtract 0.01, and 0.1. So that's how I get these. And then I'll add 0.001, add 0.01, add 0.1. So that's how I'll get my numbers that are near. So remember, I need to be very close to that, the x value, the input. Right? And now I just do substitution. I did it on a table, a calculator. So plug all these x's into here, and you'll get all the y values. And you can see now it's clear as I come in from the left, these are going to approach 2. And if it's not clear, maybe I try another one. I do 0.9999. All right, maybe you can be as accurate as you need to be. As I come in from the right, it looks like I also approach 2. So now I can see, just like my graph showed me, that the behavior as I approach 1, the y behavior, approaches 2. So the limit of this would equal 2. Okay? And again, so it's saying the behavior of this function around x equals 1 is y equals 2. All right, so let's do some notes here. So when you're finding limits using tables, do this, right? So create a table with 7 spots. All right? And then in the middle spot, I want you to put whatever that x value is from x approaches a. Put it right in the center. All right? And then go to the left side to fill in the left side. You're going to go subtract, 0.1, 0.001, 0.001. To fill in the right side, you're going to add 0.1, 0.01, 0.001. All right, and that'll be my table. So I'll have 3 spots to the left, 3 spots to the right, and something right in the middle. All right, so that's going to be the end of this video. So complete classwork problems 4 and 5.